Okay, now you should have already watched Finding Area Between Curves Part A, which was with respect to x. This one's looking at with respect to y. If you haven't watched the first one, I would recommend you go back and do that. Otherwise, this one won't make a whole lot of sense. But what we're doing it different this time is sometimes we're not able to set up a curve. Like if we look at this curve here, you'll notice that we don't have a clear top and bottom. If we try to take in top and bottom between this curve, notice it's the same curve on top and on bottom. Now sometimes we might be able to split that function up into two parts, but other times it won't be very easy or will be very inconvenient to do that. But what we can do if we keep it in terms of y, we can think about using it as right minus the left side, or the greater side minus the lesser, just so that we're always getting a positive value there. Now what you need to be careful with then is make sure that your equations are in terms of y, you integrate with respect to y, and even more importantly, because this is probably the most frequently missed thing on a problem like this, is that these values, the limits of integration, have to be the y values. Because we're slicing it this way. We're taking our height as being the x value there, because we're taking finding x with respect to y minus the different x with respect to y. And so all of these heights, again, are going that way. That's slicing the y-axis. And so these values need to be y values. Always consider that when we're setting it up using with respect to y. Now notice this is the same problem that we had in the other section we were doing with respect to x. But in this case we can actually simplify our problem. With x we had to split this into two regions because we were going from here to here, and then we were going from 2 to 4. But if I do this with respect to y, I can just do it in one shot. Notice going this way, if I think about these little rectangles, as I'm slicing the y-axis, and so that would be going from 0 to 2 on the y-axis. Again, don't use the 0 to 4. That's going to throw everything off. Okay, the next thing then is we think about the top, but we're not really using the top. These are with respect to y, and so we'll be using the right side and subtracting the left side. In this case, the left is the curve. And so our right side here is y equals x minus 2. Problem, we needed this to be in terms of y because we're slicing it this way. And so I'm going to solve this thing for x in terms of y, which gives me x equals y plus 2. Okay, that's on the right, so that's going to go first. On the left side, we have our curve. It also needs to be solved for x, and we get y squared. We close that by writing dy, because again, we're differentiating with respect to y. And when you work that out, you should find that you get the same answer that we got when we did it with respect to x. Now this isn't the only way to do it. Another way to do it is to consider geometry formulas. Now what this means is, as I look at this shape here, I notice that if I just took the integral going from 0 to 4, again, now this is doing it with respect to x because I'm going from top to bottom again. But notice that what's left over here, if I take that whole integral there going from 0 to 4, what I want to cut away is a triangle. And what is the area of that triangle? Well, the area, we have a base of 2, a height of 2, and so 1/2 of 2 times 2, or just 2. So since the integral is based on area, we can use simple geometry formulas when we see them as a valid way of solving the integral. So with this one, the main part here was going from 0 to 4. And that curve was the square root of x dx. Now notice all of those are x values. The 0 to 4 are x values, square root of x is x, and so on. Now that gives me all of this green part, but again I want to take away the triangle. So I'll just write that again. I'm using my formula for the area of the triangle. And that also should give me the same area that I got for this one, as long as I've done it correctly, and also the way that we did it in the last section. So sometimes we just have to make a choice about which one is the best thing to do. And so there's a few things we could look at. The key question is, which one's more convenient? If you look at this curve on the top here, going from C to D and A to B, notice how easy it is if we just draw it looking at going from top to bottom. I'm always, if I do it with respect to y, I'm always going from the right side to the left side. There's no point where that's a problem in there if I'm going from B to D. Okay, those are my y values there. And so my integral would, with respect to y, would be going B to D. Now I have to solve everything for y, which is going to give me the cubed root of y, which is my right one, minus, and notice this one's already in the correct form. It's already in terms of y, and so I can just leave it like that, and dy. Now let's look what would have happened if we'd used the x. First of all, we would have to split our region right here, because we wouldn't have enough space to go the whole way across. Also, if you look at this function here, you have the same function on top and bottom. This is the equation x equals y squared minus 2. If we try to solve that for x, we could do that, but it's going to end up being y squared equals x plus 2, and you need to be very careful here because this is plus or minus the square root of x plus 2. This is actually two different functions, and so we could break it up where the top function is x plus 2 minus the bottom function, which is negative square root of x plus 2. Now that would make sense that it would just be 2 times x plus the square root of x plus 2, since it should be symmetrical. But we see that we're complicating things. We've only looked at the first part there. Now if we move on to the second part, we'd have to write that out, and that would be a second integral. So we'd have to be adding two different integrals there in order to do that. And that would just complicate our problem a bit. It would be a lot easier to do this in terms of y.